Welcome to Science for Sleep, where we explore the mysteries of the universe in a calm, soothing journey designed to help you drift into peaceful rest. Tonight, we will drift through the frozen realm of Europa, Jupiter's enigmatic moon, and discuss the extraordinary ocean that lies hidden beneath its ancient ice. We will explore the possibility that life, alien life, completely unlike anything on Earth, might be swimming in those dark waters right now, just 400 million miles away in our own cosmic neighborhood. This is a journey of wonder and discovery, told slowly and gently, perfect for letting your mind wander as sleep approaches. Before we begin our voyage to this distant, frozen world, if you enjoy these deep explorations of space and science, please take a moment to like this video and subscribe to our little struggler channel, Science for Sleep. Your support helps us create more of these long-form documentaries that blend fascinating science with the perfect atmosphere for rest and reflection. And if you find yourself drifting off before the end, that's exactly what we hope for. You can always return tomorrow night to continue the journey. Now, let us begin. Close your eyes if you wish, get comfortable, and let your imagination travel with me across the solar system to a place of profound mystery and possibility, where an ocean twice the size of all Earth's seas has been waiting in darkness for billions of years, perhaps harboring the answer to humanity's oldest question: are we alone in the universe? Europa might be about to tell us. Beneath a shell of ice thicker than mountains are tall, in darkness so complete that no ray of sunlight has penetrated for billions of years, there exists an ocean that may hold the answer to humanity's oldest question. This ocean is not on Earth. It does not lap against familiar shores or reflect our sun, or feel the pull of our moon. This ocean circles a world locked in the gravitational embrace of Jupiter, the solar system's largest planet. A world where the surface temperature never rises above minus 260 degrees Fahrenheit, where radiation would kill an unprotected human in minutes, where the landscape is a frozen wasteland of ice fractured into chaotic patterns that speak of violence and movement beneath. Europa, the fourth largest moon of Jupiter, smaller than Earth's moon, but covered entirely in water ice that gleams pale and bright, has captured the imagination of scientists and dreamers, because beneath that ice lies more liquid water than exists in all of Earth's oceans combined. And where there is liquid water, where there is energy, where there are the chemical ingredients of life, there might be life itself, swimming and floating and crawling in the absolute darkness of an alien sea. The search for life in Europa's ocean represents one of the most profound scientific endeavors humanity has ever undertaken. Not because we know life is there, but because if it is there, if we find even a single microbe in those dark waters, it will prove that life is not unique to Earth, that the universe is filled with living things, that we are not alone in the cosmos. This is the story of that search, of what we know and what we suspect about Europa's hidden ocean, of the missions planned and the technologies being developed to pierce that ice shell and explore what lies beneath, and of what it would mean for humanity to discover that life has emerged twice in our own solar system, that biology is not a miracle, but a consequence of chemistry given the right conditions. This is a journey to the edge of possibility, to a place so strange and so distant that reaching it will require decades of effort and billions of dollars, and the combined genius of thousands of scientists and engineers, all in pursuit of something that may not even exist, all driven by the need to know whether we are alone. The implications of finding life on Europa would cascade through every aspect of human understanding, through science and philosophy and religion, and our sense of place in the universe. If life exists in Europa's ocean, it almost certainly arose independently from Earth life, because Europa and Earth are so different and so separated that the transfer of living organisms between them seems nearly impossible even over billions of years. Independent origin would mean that life is not a singular accident, but a natural outcome when conditions permit, that the universe is likely teeming with biology in forms we can barely imagine, on worlds we've not yet discovered, in environments we consider impossibly hostile. It would mean that our radio telescopes scanning the stars for signals from intelligent civilizations are not engaged in a fool's errand, but are participating in a search that has real probability of success. Because intelligence may evolve wherever life has enough time and complexity. It would transform astrobiology from a theoretical field to an observational science with at least 2 data points, Earth and Europa, from which we could begin to build theories about what conditions favor life, what forms it might take, how it evolves and adapts and spreads. For the religious, it would raise profound questions about creation and uniqueness, and whether divine attention is focused on humanity or distributed across countless living worlds. For the philosophers, it would challenge anthropocentric thinking and force consideration of moral status and rights for life forms that share no evolutionary history with us, that might not even be made of the same chemistry. For the dreamers, it would be confirmation that the universe is not dead and empty but alive and full of wonders waiting to be discovered. All of this potential, all of these questions and possibilities rest on whether we can pierce the ice of Europa and find in those dark waters the signature of life. Understanding Europa requires first understanding its place in the Jupiter system, because Europa cannot be understood in isolation from the massive planet it orbits and the other moons that share its neighborhood. Jupiter is the giant of our solar system, containing more mass than all other planets combined. A world so large that 11 Earths could fit across its diameter, and over 1,300 Earths could fit inside its volume. Jupiter is primarily made of hydrogen and helium, gases compressed by gravity into a liquid state deep in the planet's interior, possibly surrounding a core of rock and ice at the center. The planet rotates rapidly, completing a full rotation in less than 10 hours, despite its immense size. And this rapid rotation, combined with internal heat, creates powerful weather systems, including storms that dwarf Earth entirely, and zones of clouds that circle the planet in bands of different colors. The most famous feature is the Great Red Spot, a storm system that has been raging for at least 400 years since telescopes first observed it, large enough to swallow multiple Earths. Jupiter generates strong magnetic fields, far stronger than Earth's, and these fields trap charged particles from the solar wind and from volcanic eruptions on Jupiter's moon Io, creating intense radiation belts that will be deadly to spacecraft and astronauts that venture too close. Europa orbits Jupiter at a distance of about 420,000 miles, completing each orbit in roughly 3.5 Earth days. This is much closer to Jupiter than our moon is to Earth, close enough that Jupiter fills Europa's sky with a presence that would dominate the view if anyone could stand on Europa's surface and look up. From Europa, Jupiter would appear almost 24 times larger in diameter than the moon appears from Earth, a massive sphere showing bands and storms and details visible to the naked eye. But no one on Europa would see this view because Europa is tidally locked to Jupiter, meaning the same face of Europa always points toward Jupiter, just as the same face of our moon always points toward Earth. From one hemisphere of Europa, Jupiter would hang permanently in the sky, moving slightly due to Europa's orbital variations, but never rising or setting. From the other hemisphere, Jupiter would never be visible at all, remaining forever below the horizon. This tidal locking is not coincidental, but is the result of gravitational interactions over billions of years that have slowed Europa's rotation until it matches its orbital period. Europa is the fourth largest of Jupiter's moons, with a diameter of about 1,940 miles, slightly smaller than Earth's moon, which has a diameter of about 2,100 miles. This makes Europa one of the smaller worlds in the solar system that we consider interesting for astrobiology, but size is less important than composition and internal structure. Europa's surface is predominantly water ice, extraordinarily pure water ice with relatively little rock or dust contaminating it, giving the surface a bright reflective quality that makes Europa one of the most reflective objects in the solar system. The surface temperature varies depending on whether a particular area is in sunlight or shadow, and how close it is to the poles, but temperatures range from about minus 260 degrees Fahrenheit on the night side to minus 370 degrees Fahrenheit in permanently shadowed polar regions. These are temperatures at which water ice becomes as hard as granite, at which materials behave in ways that are alien to our Earth experience, where ice is something that melts in your hand and cracks under pressure. On Europa, the ice shell is essentially rock, but rock that can flow very slowly over geological time, rock that records stresses and movements in cracks and ridges and chaos regions that cover the surface. The surface features of Europa are among the strangest in the solar system and provide the primary evidence that led scientists to hypothesize the existence of the subsurface ocean. Europa has very few impact craters compared to other moons and planets, suggesting that the surface is young in geological terms, probably less than 100 million years old, and possibly much younger. This is extraordinary because most solid surfaces in the solar system are ancient and heavily cratered from billions of years of impacts. A young surface implies that something is renewing or resurfacing Europa, erasing old craters through geological activity. The surface is crisscrossed with long linear features called lineae, cracks or fractures in the ice that can extend for thousands of miles and can be several miles wide. Some of these fractures show evidence of having opened and then been filled with fresh ice from below, creating double ridges with a central valley, or creating smooth bands where the crack filled completely. The fracture patterns suggest that the ice shell is flexing and cracking in response to tidal stresses, that it is not rigidly locked to the interior but can move and flex. The most dramatic features are the chaos terrains, regions where the normal linear fracture patterns break down into a jumbled mess of ice blocks that appear to have broken apart, rotated, and refrozen in new positions. These chaos regions look remarkably like broken pack ice on Earth's polar oceans, like ice flows that have been pushed around by currents before refreezing. The analogy is probably accurate. The chaos terrains likely form when the ice shell is weakened or melted from below, allowing the surface to break into pieces that float and drift in liquid water or slush before the water refreezes and locks them in place. Some chaos regions show evidence that the ice blocks have moved significant distances, with features on adjacent blocks not matching up the way they would if the blocks had simply cracked in place. Material from below appears to have erupted into some chaos regions, bringing darker material up to the surface and creating areas that are less reflective than the pure ice surrounding them. All of these features, the young surface, the fracture patterns, the chaos terrains, the evidence of material moving from below, point to an active geology driven by something beneath the ice shell. The hypothesis that Europa contains a global ocean beneath its ice shell emerged gradually through observations and theoretical modeling over several decades. Early observations from Earth-based telescopes and the Pioneer and Voyager spacecraft that flew past Jupiter in the 1970s and 80s showed that Europa was an icy world with an unusually smooth surface and interesting fracture patterns. But these initial observations could not penetrate below the surface or determine the internal structure. The breakthrough came with the Galileo spacecraft, which arrived at Jupiter in 1995 and spent 8 years studying the Jupiter system with multiple flybys of Europa and the other major moons. Galileo carried instruments that could measure magnetic fields, gravitational variations, surface composition, and could image the surface at much higher resolution than previous missions. The data from Galileo transformed Europa from an interesting curiosity to the primary target for astrobiology in the outer solar system. The magnetic field measurements were particularly compelling. As Galileo passed near Europa, its magnetometer detected variations in the magnetic field that could be explained by an electrically conductive layer inside Europa, responding to Jupiter's powerful rotating magnetic field. When Jupiter's magnetic field sweeps across Europa as Jupiter rotates, it induces electric currents in any conductive material inside Europa, and these currents generate their own magnetic field that Galileo could detect. The strength and pattern of the induced magnetic field allowed scientists to calculate how conductive the layer must be and how deep it must be. The results pointed to a layer of salty liquid water which conducts electricity well, rather than solid ice, which does not conduct. The induced magnetic field was too strong to be explained by a small pocket of water. It required a global ocean extending all the way around Europa beneath the ice shell. This magnetic evidence provided strong indirect proof that Europa contains more liquid water than all of Earth's oceans, locked beneath a frozen lid and hidden from direct observation. Gravitational measurements supported the ocean hypothesis by revealing Europa's internal structure in layers. When spacecraft fly past a moon or planet, the gravitational pull of that body affects the spacecraft's trajectory in ways that can be measured with extreme precision by tracking radio signals from the spacecraft. Variations in gravity reveal variations in mass distribution inside the body, allowing scientists to build models of the internal structure. For Europa, the gravity measurements show that the Moon is differentiated into layers with denser material in the center and less dense material toward the surface. The best fit to the data suggests that Europa has a metallic iron core at the center, surrounded by a rocky mantle, which is in turn surrounded by a layer of water or ice about 60 to 100 miles thick. This water layer is far too thick to be solid ice all the way through, given what we know about ice behavior under pressure and temperature. The most likely structure is a relatively thin ice shell, probably 10 to 15 miles thick, but possibly as thin as a few miles in some locations, or as thick as 30 miles, floating on top of a liquid ocean that could be 50 to 100 miles deep. Below the ocean is the rocky mantle, and the boundary between liquid water and rock is of intense interest, because it is there that interesting chemistry could occur. The tidal heating mechanism that keeps Europa's ocean liquid, despite the intense cold, is one of the most elegant pieces of planetary physics. Europa orbits Jupiter in an elliptical path rather than a perfect circle, and this elliptical orbit is maintained by gravitational interactions with Jupiter's other large moons, particularly Io and Ganymede, which are in orbital resonance with Europa. For every orbit Europa makes, Io makes exactly 2 orbits, and Ganymede makes exactly half an orbit, and this mathematical relationship creates regular gravitational tugs that prevent Europa's orbit from becoming perfectly circular. The elliptical orbit means that Europa's distance from Jupiter varies during each orbit. And since tidal forces depend on distance, the strength of Jupiter's gravitational pull on Europa varies throughout each orbit. When Europa is closer to Jupiter, the tidal forces are stronger and the Moon is stretched slightly in the direction toward and away from Jupiter. When Europa is farther away, the tidal forces are weaker and Europa relaxes slightly. This constant flexing and relaxing as Europa orbits generates friction inside the Moon, and friction generates heat. The same way bending a wire back and forth rapidly makes it hot. The amount of heat generated depends on how much flexing occurs and on the internal properties of Europa, particularly whether there is a liquid layer that can deform more easily than solid ice or rock. The calculated tidal heating is sufficient to generate heat flows comparable to Earth's geothermal heat flow, enough to keep a subsurface ocean liquid despite surface temperatures hundreds of degrees below freezing. The heat is probably not uniformly distributed, but may be concentrated in certain regions or at certain depths, potentially creating areas of warmer water or even hydrothermal activity where heated water circulates through cracks in the rocky mantle. On Earth, hydrothermal vents on the ocean floor support rich ecosystems in complete darkness, with bacteria and archaea forming the base of the food chain by extracting energy from chemicals in the hot water rather than from sunlight. If Europa has similar hydrothermal systems, they could potentially support ecosystems as well, by providing not just heat, but also chemical energy and nutrients from the rock-water interactions. This possibility makes Europa not just a world with water, but a world that might have the three key requirements for life as we understand it: liquid water, energy sources, and organic chemistry. Understanding whether Europa's ocean could support life requires understanding what life needs at a fundamental level. Life on Earth, in all its enormous diversity from bacteria to blue whales, shares certain requirements that appear to be universal consequences of how biochemistry works. First, life needs liquid water as a solvent, a medium in which molecules can dissolve and move and interact. Water has unique properties that make it ideal for biochemistry, including its ability to dissolve both polar and non-polar substances. Its temperature range as a liquid under common planetary conditions, its role in many chemical reactions, and its unusual property of being less dense as ice than as liquid, which allows ice to float and protects liquid water below. While some theoretical studies suggest that other liquids like ammonia or methane could potentially support exotic forms of life, all known life uses water, and the search for life elsewhere naturally focuses on finding liquid water. Second, life needs energy to drive the chemical reactions that maintain living systems against the tendency toward disorder and decay. On Earth's surface, most ecosystems ultimately derive their energy from sunlight through photosynthesis, with plants and algae capturing solar energy and converting it to chemical energy that flows through food webs as organisms eat and are eaten. But sunlight is not the only possible energy source. In the deep ocean, far from sunlight, hydrothermal vent ecosystems derive their energy from chemical reactions between hot water and minerals, a process called chemosynthesis. Bacteria use the chemical energy in compounds like hydrogen sulfide and methane to build organic molecules. And these bacteria support communities of animals that could not exist without this chemical energy source. Europa's ocean, completely isolated from sunlight by miles of ice, would need to depend entirely on chemical energy, either from hydrothermal activity at the ocean floor or from chemical reactions involving the ice and ocean water. Third, life needs raw materials to build its structures and machinery, specifically the elements carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, which make up the bulk of biological molecules, along with various trace elements like iron, magnesium, and zinc that serve as cofactors in enzymes. Earth life is carbon-based, meaning that organic molecules with carbon-carbon or carbon-hydrogen bonds form the structural and functional molecules of life, including proteins, nucleic acids, carbohydrates, and lipids. Carbon is uniquely suited for this role because it forms stable bonds in long chains and complex structures and can bond with many other elements, creating the chemical diversity that biochemistry requires. Europa almost certainly has abundant oxygen in the form of water and ice, and has hydrogen in the same water molecules. The presence of carbon, nitrogen, sulfur, and phosphorus is less certain but likely. Spectroscopic observations of Europa's surface have detected signs of salts, including magnesium sulfate and sodium chloride, suggesting that sulfur and sodium are present. Some of the darker non-ice material on Europa's surface may be organic compounds, carbon-based molecules delivered by comets and asteroids over billions of years, or possibly generated by radiation processing of simpler molecules. The radiation environment at Europa is both a challenge and potentially a resource for chemistry. Jupiter's powerful magnetic field traps charge particles, creating radiation belts far more intense than Earth's Van Allen belts. Europa orbits within these radiation belts and is constantly bombarded by high-energy electrons and ions that slam into the surface ice. This radiation breaks apart water molecules in a process called radiolysis, by splitting water into hydrogen and oxygen. The hydrogen, being light, can escape Europa's weak gravity and be lost to space, while the oxygen remains and can react with other materials or can be incorporated into the ice. Over time, radiolysis has probably created a significant amount of free oxygen at and below Europa's surface. This oxygen could potentially make its way into the ocean, creating an oxygen-rich environment that would be unusual for a dark ocean, but could support more complex and energetic forms of life than anoxic environments typically do. Alternatively, the oxygen could react with organic molecules, with metals in the ice, or could remain frozen in the ice as molecular oxygen or hydrogen peroxide. The ocean chemistry would be determined by interactions between water, ice, rock, and any compounds delivered from the surface or from the rocky interior. The ocean is probably salty, similar to Earth's oceans, because water dissolves salts from the rocky mantle as it circulates through cracks and porous regions. The exact composition of the salts is unknown, but likely includes sodium chloride, magnesium sulfate, potassium chloride, and possibly other compounds. The pH could range from acidic to basic, depending on what minerals are dissolving and what gases are present. And the pH affects what chemistry is possible and what forms of life could survive. The temperature would vary with depth and location, probably hovering around the freezing point of the salty water near the base of the ice shell, perhaps minus 10 degrees Fahrenheit, or colder depending on salt concentration, and potentially much warmer near hydrothermal vents if they exist. The pressure at the ocean floor would be enormous, perhaps 15,000 to 30,000 pounds per square inch, depending on ocean depth. Pressures comparable to the deepest parts of Earth's oceans. But pressure alone does not prevent life, as Earth's deep ocean ecosystems demonstrate. If life exists in Europa's ocean, it would need to survive in conditions radically different from most of Earth's biosphere. The complete absence of sunlight is perhaps the most obvious challenge. Photosynthesis, the process that powers most of Earth's ecosystems and produces the oxygen we breathe, would be impossible in Europa's ocean. Any life there would need to be based entirely on chemical energy, functioning more like Earth's deep ocean vent communities than like familiar surface ecosystems. This is not impossible. Chemosynthetic life is abundant on Earth and may even be older than photosynthetic life. But it does limit the amount of energy available and thus potentially limits the complexity and abundance of life that the ecosystem could support. On Earth, chemosynthetic ecosystems are localized around energy sources like hydrothermal vents, and biomass density drops off rapidly with distance from these energy sources. A Europa ocean with limited and localized chemical energy sources might similarly have sparse life clustered around whatever vents or chemical gradients provide energy, with vast volumes of the ocean being essentially empty of life. The cold temperature, while challenging, is not necessarily a barrier to life. Earth has psychrophiles, cold-loving organisms that thrive in permanently frozen environments, including Antarctic ice, Arctic permafrost, and deep ocean water near freezing. These organisms have adaptations that allow their biochemistry to function at temperatures that would shut down most life, including enzymes that remain flexible and active in the cold and cell membranes that stay fluid rather than freezing solid. Europa's ocean temperature is likely colder than most Earth-ocean environments, but probably not so cold as to be fundamentally incompatible with life, especially if there are warmer regions near hydrothermal activity. The high pressure would also not necessarily prevent life, as demonstrated by organisms in Earth's Hadal zone, the deepest ocean trenches where pressures exceed 15,000 pounds per square inch. These organisms have adaptations in their cellular structure and proteins that allow them to function under crushing pressure that would kill shallow water organisms. The isolation from the surface and from any external input of organic material would be a more significant challenge. On Earth, even the deepest ocean ecosystems receive some input of organic matter from above. Dead organisms and fecal material and other organic particles that drift down from the sunlit surface layers where photosynthesis produces them. This organic rain supplements the chemical energy available to deep ocean life. Europa's ocean would have no such input from above, or at most a tiny input if organic material from the surface can somehow work its way through miles of ice to reach the ocean. The ecosystem would need to be completely self-sustaining, based only on energy and materials available in the ocean and from the rocky floor. This probably means a simpler and less productive ecosystem than Earth's oceans, possibly consisting only of microbial life without the multicellular animals and plants that characterize Earth's diverse ecosystems. But microbial life can be remarkably diverse and can occupy every available niche where energy and materials allow metabolism to occur. On Earth, microbes live in environments that would be instantly fatal to complex life, including in boiling hot springs, in concentrated acid, in saturated salt, in solid rock miles below the surface, in toxic heavy metal solutions, in the water cores of nuclear reactors. If the basic requirements of water, energy, and chemistry are met in Europa's ocean, there is no obvious reason why life could not emerge and persist there. The question is not whether the environment is too extreme for life as we know it, because we know that microbial life can tolerate extreme conditions, but whether the environment provides enough energy to sustain metabolism and reproduction over the timescales necessary for life to originate and evolve. The origin of life is still poorly understood even for Earth, but most theories require concentrated sources of energy and organic molecules, conditions that might exist at hydrothermal vents or in other special environments, but might not exist everywhere in Europa's ocean. Exploring Europa and searching for life in its hidden ocean requires sending spacecraft on missions that are among the most challenging and expensive ever attempted. The Galileo mission provided the foundational data that established Europa as a high-priority target, but Galileo was designed to study the entire Jupiter system and could only dedicate a fraction of its resources to Europa. The spacecraft made multiple flybys of Europa, approaching as close as 125 miles from the surface. But each flyby lasted only hours, and the total time Galileo spent near Europa amounted to days across the entire mission. The radiation environment limited how long Galileo could safely operate in the inner Jupiter system, and the spacecraft's instruments were not designed specifically for Europa investigations. Despite these limitations, Galileo revolutionized our understanding of Europa and demonstrated that dedicated missions could learn far more. NASA's Europa Clipper mission, scheduled to launch in the mid-2020s, represents the next major step in Europa exploration. Clipper is not a lander or an orbiter, but a spacecraft designed to make multiple flybys of Europa while in orbit around Jupiter. This mission architecture was chosen because orbiting Europa directly would subject the spacecraft to years of intense radiation that would gradually damage electronics and instruments, shortening the mission lifetime. By orbiting Jupiter instead and only passing near Europa during brief flybys, Clipper can study Europa intensively while spending most of its time at safer distances where radiation levels are lower. The mission plan calls for approximately 50 flybys over a 4-year primary mission, with flybys at various altitudes from as low as 15 miles to as high as 1,800 miles above the surface. Each flyby will last only a few hours, but the spacecraft will be able to image different areas of the surface at high resolution, measure the ice shell thickness using ice-penetrating radar, sample the composition of the surface and any plumes of water vapor that might be erupting through the ice, and measure the magnetic and gravitational fields to constrain the ocean's properties. The Europa Clipper spacecraft is large and complex, with a dry mass of about 7,200 pounds, not including fuel, making it one of the largest planetary science missions NASA has flown. The size is driven partly by the need for substantial shielding to protect sensitive electronics from radiation, and partly by the power requirements for the instruments and for communications across the vast distance from Jupiter to Earth. The spacecraft carries 9 scientific instruments, including cameras, spectrometers, a magnetometer, a gravity and radio science package, a thermal emission imager, and an ice-penetrating radar called Reason that will use radio waves to probe the ice shell and potentially detect the boundary between ice and liquid water. One instrument, called SUDA, will analyze particles of dust and water ice ejected from Europa's surface by micrometeorite impacts, looking for the chemical signatures of organic molecules and salts from the ocean. Another, called Europa UVS, is an ultraviolet spectrograph that will search for plumes of water vapor erupting from the surface, similar to the plumes observed at Saturn's moon Enceladus by the Cassini spacecraft. The plume observations are particularly exciting because if Europa is occasionally venting ocean water through cracks in the ice, a spacecraft could potentially sample that ocean water without needing to land or drill through the ice. The Hubble Space Telescope has reported possible detections of water vapor plumes at Europa on several occasions. Though the observations are at the limit of the telescope's capabilities, and the plumes, if real, appear to be intermittent rather than continuous. Europa Clipper will search for plumes during multiple flybys, and if plumes are detected, the spacecraft could fly through them and directly sample particles and gases from the ocean. This would allow chemical analysis of ocean composition, including salinity, pH, dissolved gases, and potentially even organic molecules or other biosignatures if they are present. Finding complex organic molecules in plume samples would not prove the existence of life. Organic chemistry can occur without biology, but it would show that the ocean has the raw materials for life and would guide future missions on where and how to search for life more directly. The European Space Agency is developing its own mission to the Jupiter system called JUICE, the Jupiter Icy Moons Explorer, which launched in 2023 and will arrive at Jupiter in 2031 after a long cruise through the solar system, including gravitational assists at Earth and Venus. JUICE will study Jupiter and 3 of its large moons, including Europa, Ganymede, and Callisto, with a mission profile similar to Clipper involving multiple flybys of each moon. JUICE will eventually enter orbit around Ganymede, becoming the first spacecraft to orbit a moon other than Earth's moon. While JUICE's primary focus is Ganymede, which also appears to have a subsurface ocean, the spacecraft will perform 2 close flybys of Europa and will contribute to our understanding of Europa's ice shell surface composition and interaction with Jupiter's magnetic field. The combination of data from both Europa Clipper and JUICE will provide a comprehensive picture of Europa's surface and subsurface structure, and will identify the best locations for future lander missions. The ultimate goal for Europa exploration is to land on the surface, to deploy instruments that can analyze the ice and potentially even drill or melt through the ice shell to access the ocean directly. Landing on Europa would be extraordinarily challenging for multiple reasons, including the radiation environment, the limited landing opportunities during the mission design, the need for autonomous landing systems, because communication delay makes real-time control from Earth impossible, and the uncertain nature of the surface itself. Europa's surface might be solid and flat in some areas, allowing safe landing, but in other areas might be rough chaos terrain or might be covered in penitentes, tall blade-like structures of ice that form in certain conditions and that could be hazardous to landers. The surface ice might be hard as rock or might be soft and fluffy in some regions, and without direct measurements, we cannot predict exactly what a lander would encounter. NASA has studied concepts for a Europa lander mission, with designs that would use a vault to protect critical electronics from radiation, would use autonomous hazard avoidance systems to select safe landing sites during descent, and would carry a sophisticated suite of instruments designed to search for biosignatures. The proposed science payload includes cameras and spectrometers to analyze surface composition, seismometers to detect icequakes and ocean currents, a microscope to examine ice crystals and any particles at very high magnification, looking for structures that might indicate biological origin, and a sampling system that could collect material from several centimeters below the surface, where radiation damage is less severe. The lander would operate on the surface for perhaps 20 to 40 days, limited by radiation damage to electronics and by the available power from batteries, or possibly a small nuclear power source. During this time, it would conduct intensive analysis of samples, looking for organic molecules, for specific ratios of isotopes that might indicate biological processing, for molecular structures that are characteristic of life, and for anything unexpected that might be a sign of present or past life. The most ambitious concept for Europa exploration would involve a cryobot, a probe designed to melt its way through the ice shell to reach the ocean directly. This technology is being developed and tested in Earth's polar regions and in laboratories, with prototypes that use heat from nuclear power sources or from electrical heaters to melt ice and descend through it, maintaining a thin meltwater film around the probe that allows it to sink gradually under its own weight. A cryobot for Europa would need to descend perhaps 10 to 30 miles through ice, a journey that could take months or years depending on the power available and the descent rate achieved. The probe would need to maintain communication with a surface, lander or orbiter, probably using a thin fiber optic cable that pays out behind it as it descends, because radio signals cannot penetrate through miles of ice. The technical challenges are enormous, including preventing the hole from refreezing behind the probe, maintaining navigation and knowing the probe's depth and position, surviving the increasing pressure as it descends, and transitioning from ice to liquid water without flooding or losing power. If a cryobot successfully reached the ocean, it could deploy a smaller submarine probe, sometimes called a hydrobot, that would explore the waters beneath the ice. This hydrobot would be one of the most sophisticated robotic vehicles ever built, needing to operate autonomously in a completely unknown environment with no direct control from Earth and probably only intermittent communication, even with the surface lander through the long tether. The Hydrobot would carry cameras, though the ocean is probably completely dark, requiring artificial lighting that would illuminate only a small volume. Sonar for mapping and navigation, water sampling systems, instruments to measure temperature, pressure, salinity, dissolved gases, and sensors designed to detect biosignatures. It might search for hydrothermal vents by following temperature or chemical gradients, or might simply explore the water column, documenting whatever exists in the ocean. The duration of such a mission would be limited by power, probably to days or weeks at most, but even a brief glimpse of Europa's ocean will be transformative for our understanding of this world and the potential for life there. The discovery of life in Europa's ocean would be one of the most significant scientific discoveries in human history. Comparable to understanding that Earth orbits the Sun, to discovering evolution by natural selection, to revealing the structure of DNA, to detecting gravitational waves or the Higgs boson. It would fundamentally change our understanding of biology from a specific phenomenon that occurred on Earth to a general phenomenon that occurs wherever conditions permit. The implications would ripple through multiple fields of science and would affect how we view ourselves and our place in the universe. In astrobiology, the field would transition from speculation to having two examples of life to study and compare. Scientists could begin to identify which features of Earth life are universal consequences of biochemistry and physics, and which are accidents of Earth's particular history. Are all living things carbon-based? Or is that specific to Earth? Do all living things use water as a solvent, or can other liquids work? Do all living things store genetic information in molecules like DNA and RNA? Or are there other biochemical solutions to information storage and heredity? If Europa life uses the same genetic code as Earth life, the same DNA or RNA structure, the same amino acids and proteins, that would suggest either that life on Europa and Earth share a common origin through panspermia, the transfer of life between worlds on meteorites, or that there is something deeply fundamental about these molecules that makes them the only or best solution to the challenges of life. If Europa life uses completely different chemistry, different amino acids, or different information molecules, that would demonstrate that life is more flexible and diverse than we imagined, and that the specific solutions Earth life evolved are not unique or necessary. The comparison would teach us what is essential for life and what is contingent, which would inform the search for life elsewhere in the universe, including on Mars, on Saturn's moon Titan, on exoplanets orbiting distant stars. It would help us design better instruments and missions for detecting biosignatures, and would help us interpret ambiguous results where we find suggestive evidence but not definitive proof of life. The existence of life in Europa's ocean would also inform the Drake equation, the famous calculation that attempts to estimate the number of communicative civilizations in our galaxy. The Drake equation multiplies together several factors, including the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction of suitable planets where life actually arises, the fraction of life-bearing planets that develop intelligent life, and so on. Many of these factors are now being constrained by astronomical observations. We know that most stars have planets, and that rocky planets in habitable zones are common. But the factor that asks what fraction of suitable planets develop life has no observational basis yet. It is pure speculation based on the single example of Earth. If life exists on Europa, that would suggest that the origin of life is relatively easy and common, at least in environments with liquid water and chemical energy, which would make the fraction higher and would increase the estimated number of life-bearing worlds in the galaxy, potentially into the billions. It would make the search for intelligent life more hopeful, because if life is common, then given enough time, intelligence might evolve on many worlds. Philosophically and culturally, the discovery would challenge human exceptionalism and would force a broader perspective on life and consciousness. For millennia, humans have considered ourselves special, created in the image of God according to some religious traditions, the pinnacle of evolution, the only beings with language and culture and technology and self-awareness. The discovery of life elsewhere, even microbial life, would show that we are not unique, that biology is a natural process that occurs in many places, that the universe does not revolve around humanity. Some would find this humbling and would draw inspiration from being part of a larger living cosmos. Others might find it disturbing or might question long-held beliefs about humanity's role and purpose. Religious traditions would need to grapple with the theological implications of life beyond Earth, and would need to consider whether their creation stories and salvation narratives apply to other living beings or are specific to humanity. These are not abstract questions, but would become urgent as evidence of Europa life is analyzed and debated. One of the most difficult challenges in exploring Europa is ensuring that we do not contaminate the ocean with Earth microbes that hitchhike on our spacecraft. This concern, called planetary protection, is taken extremely seriously by space agencies because the consequences of contamination could be severe both scientifically and ethically. Scientifically, if we introduce Earth life to Europa and it survives and spreads, we might later discover life on Europa and not be able to determine whether it is native Europa life or descendants of Earth contamination. This would ruin Europa as a natural laboratory for studying independent origin of life, and would make any biosignatures we detect ambiguous and uncertain. Ethically, if native Europa life exists, introducing Earth microbes could potentially harm or destroy that native biosphere, especially if Earth microbes are better competitors, or if they introduce diseases or metabolic pathways that disrupt the existing ecosystem. This would be an act of biological imperialism, of destroying something unique and irreplaceable through carelessness or negligence. All spacecraft sent to Europa are rigorously cleaned and sterilized before launch using procedures called planetary protection protocols. These protocols specify how hardware must be built, what materials can be used, how components must be cleaned with solvents and heat, how spacecraft are assembled in clean rooms with filtered air and workers in protective suits, and how the final spacecraft is sterilized with heat or radiation before being sealed for launch. The goal is to reduce the number of viable microbes on the spacecraft to levels where the probability of contaminating Europa is acceptably low, typically defined as less than 1 chance in 10,000 of introducing a viable microbe to the ocean during the mission lifetime. And even with rigorous sterilization, completely eliminating all microbes is impossible because some organisms form hardy spores that can survive extreme conditions, and because spacecraft have complex internal structures and materials that cannot be sterilized without damaging them. The strategy is to reduce the microbial load to very low levels, and then to rely on additional barriers to prevent any surviving microbes from reaching potentially habitable environments. For missions that will only fly past or orbit Europa, the main planetary protection concern is accidental impact, the possibility that the spacecraft could malfunction and crash into Europa. Mission designs incorporate this concern by ensuring that even after the spacecraft runs out of fuel and can no longer be controlled, its trajectory will not intersect Europa. Europa Clipper, for example, will end its mission by crashing into Ganymede, another Jovian moon that is also interesting for astrobiology, but is considered lower priority than Europa, or will crash into Jupiter itself, ensuring that the spacecraft cannot drift and eventually impact Europa. For lander missions, the concern is more direct because the lander will by design contact Europa's surface. Lander sterilization requirements are much more stringent, and mission designs must ensure that the lander does not expose the ocean to contamination even if it partially breaks through the ice, or if microbes can migrate through the ice from the landing site. For missions that would drill or melt through the ice to access the ocean, planetary protection becomes extraordinarily challenging because the mission explicitly intends to cross the barrier between the external environment and the ocean that might harbor life. Such missions would require sterilization protocols beyond anything previously achieved, possibly including terminal sterilization of the probe shortly before it enters the ocean, using heat or radiation or chemicals to kill any surviving microbes at the last moment before the probe transitions from ice to water. This terminal sterilization must not damage the probe's scientific instruments or systems, but must be effective against hardy organisms, including extremophiles, that might survive the earlier sterilization processes. Some scientists argue that drilling to Europa's ocean should not be attempted until we have better understood the surface and ice shell, and have confirmed through multiple missions that life is likely to exist, making the risk of contamination worth the potential reward of direct detection. Others argue that the ocean is the only place where definitive detection of life is possible, and that we should proceed with drilling as soon as the technology is mature, accepting that some risk of contamination is unavoidable but manageable. Assuming missions to Europa can avoid contamination and can successfully analyze materials from the ice, surface, or ocean. the challenge becomes recognizing life if it exists. This is more difficult than it might seem, because life is hard to define rigorously, and because the biosignatures we are familiar with from Earth life might not apply to Europa life if it has a different biochemistry. On Earth, we recognize life through multiple converging lines of evidence, including visual observation of cells or multicellular organisms, detection of metabolic activity such as consumption of nutrients and production of waste, detection of reproduction and growth, detection of complex organic molecules, especially those that are characteristic of biological processes, and detection of isotopic fractionation, where biological processes preferentially use lighter isotopes of elements like carbon and nitrogen. No single observation is definitive, but when multiple biosignatures are present and alternative non-biological explanations can be ruled out, the conclusion that life is present becomes strong. For Europa, visual identification of life would require imaging at microscopic scales and would require recognizing structures that look biological even if they do not look like any Earth organism. Microbial life on Europa might not have cell walls, or might have structures quite different from Earth bacteria or archaea. It might not move, or might move in ways that are not obviously purposeful. It might be sparse rather than forming visible colonies or biofilms. Distinguishing microscopic life from abiotic structures like ice crystals or mineral grains would require careful analysis of morphology, of internal structure if the organisms can be dissected or sectioned, and of chemical composition. Terrestrial microbes have specific morphologies, including shapes like rods, spheres, spirals, filaments, and have internal organization, including membranes, genetic material, ribosomes, and other structures visible with electron microscopy. Europa life might have analogous structures that serve similar functions, even if they look different in detail. Chemical biosignatures would likely be more reliable than morphology because chemistry reflects function and metabolism. All known life is made of organic molecules, carbon-based compounds, and produces specific classes of organics, including amino acids, lipids, sugars, and nucleotides. The presence of these molecules in samples from Europa would be suggestive, though not conclusive, because some organic molecules can form through abiotic processes. What makes organic molecules biosignatures is the presence of complexity, of specific patterns that are characteristic of biology. For example, Earth life uses only 20 amino acids in proteins out of the hundreds of possible amino acids, and uses only left-handed versions of those amino acids due to evolutionary history. Finding a mixture of amino acids with this specific pattern would be strong evidence for life. Similarly, lipids in cell membranes have specific structures and compositions that differ from abiotic lipids. Polymers, long chains of molecules like proteins and nucleic acids, are characteristic of biology because abiotic chemistry rarely produces long regular polymers. Isotopic ratios provide another class of biosignatures, because metabolic processes often preferentially use lighter isotopes of elements, leaving characteristic signatures in biological materials. Carbon has two stable isotopes, carbon-12 and carbon-13, and photosynthetic organisms preferentially incorporate carbon-12 into organic molecules, leaving the organic material depleted in carbon-13 compared to inorganic carbon sources. This fractionation can be measured with high precision and has been used to identify biological activity in ancient Earth rocks and even in meteorites, where biogenic origin is debated. Europa life, if it uses carbon-based biochemistry, would likely also fractionate carbon isotopes, though the magnitude and direction of fractionation might differ from Earth organisms depending on the metabolic pathways used. Finding organic material with isotopic ratios that differ significantly from inorganic material and that show the characteristic patterns of biological fractionation would be strong evidence for life even without identifying specific organisms. Metabolic activity, if it could be measured directly, would provide compelling evidence for life, because metabolism is a defining characteristic of living systems. On Earth, metabolic activity can be detected by measuring consumption of nutrients and production of waste products, by measuring heat generation, by measuring movement or growth, or by detecting specific enzymes or metabolic products. For Europa samples, metabolic activity might be detected by incubating samples with various nutrients labeled with isotopic tracers, and then measuring whether the tracers are incorporated into organic molecules or released as gases. If samples from Europa show metabolic activity when provided with energy sources and nutrients, especially if the activity is specific to certain compounds or ceases when sterilized, that would be strong evidence for living organisms. The challenge is that metabolism might be slow in the cold conditions, might require chemical conditions we do not provide in the experiments, or might use metabolic pathways we do not anticipate and thus do not test for. Most discussions of Europa life focus on microbes because microbial life is simpler, requires less energy, and can survive in a wider range of conditions than complex multicellular life. On Earth, microbial life dominated for the first 3 billion years of life's history, with complex multicellular organisms appearing only in the last 15% of Earth's history. But the possibility of complex life on Europa cannot be entirely dismissed, even if it seems less likely. If Europa's ocean has existed for billions of years, if chemical energy sources are abundant enough, if the environment is stable enough to allow evolution to explore diverse strategies, then it is conceivable that life could have evolved beyond the microbial stage to produce more complex organisms. These would probably not resemble Earth animals because the evolution would be entirely independent and the environmental constraints would be radically different. But they might fill some similar ecological niches. On Earth, the deep ocean hosts a variety of complex life adapted to darkness and cold, including fish, crustaceans, worms, and other invertebrates. These organisms have evolved remarkable adaptations, including bioluminescence to create light for communication and hunting, enlarged eyes or other senses to detect faint cues in the darkness, slow metabolisms to conserve energy in the food-poor environment, and specialized feeding strategies to exploit whatever food sources are available. Europa organisms, if they exist and have evolved complexity might have parallel adaptations. They might use bioluminescence or might rely entirely on non-visual senses like chemoreception or mechanoreception to detect chemical gradients, currents, and vibrations. They might be slow-moving or sessile, conserving energy and waiting for food to drift by rather than actively hunting. They might be very different in scale from Earth organisms, possibly microscopic multicellular organisms rather than centimeter or meter scale animals. The amount of chemical energy available would likely limit the size and abundance of complex life. Earth's deep ocean ecosystems support relatively high biomass around hydrothermal vents, but biomass decreases rapidly with distance from vents, and many areas of the deep ocean are essentially barren. If Europa's ocean has only limited and localized energy sources, complex life might be restricted to small areas near vents, with the vast majority of the ocean being effectively empty or supporting only sparse microbial life. The food web would be short, probably just chemosynthetic bacteria and perhaps a few grazing organisms that feed on the bacteria, without the elaborate multi-level food webs that characterize productive Earth ecosystems. Large predators like fish would be unlikely because there would not be enough prey to support them. The largest organisms might be comparable to Earth's tube worms that cluster around hydrothermal vents, sessile animals that filter feed on bacteria, and suspended organic material in the water. The discovery of complex life on Europa would be even more significant than finding microbes, because it would demonstrate that the evolutionary pathways to complexity and the development of multicellular organisms are not unique to Earth, that given enough time and stability, life tends to evolve toward greater complexity. It would show that the principles of evolutionary biology, including natural selection, adaptation, and ecological interactions, operate on other worlds and produce similar outcomes, even with different starting biochemistry. It would make the existence of intelligent life in the universe seem more probable, because intelligence on Earth emerged from the evolution of complex multicellular life. And if that evolutionary progression is natural and repeatable, then intelligence might emerge on many worlds where life has enough time to evolve complexity. But the absence of complex life on Europa would not be surprising and would not argue against the presence of microbial life, because microbial ecosystems can persist and function for billions of years without necessarily producing complex organisms, especially in energy-limited environments. Predicting when we might discover life on Europa, if it exists, requires considering the timeline for missions and the capabilities of planned instruments. Europa Clipper will arrive at Jupiter in 2030 and will begin its Europa Science mission in 2031, conducting flybys over several years. If plumes are detected and sampled, preliminary data could be available by 2032 or 2033, and detailed analysis might take additional years as scientists work through the complex data looking for organic molecules and biosignatures. If no plumes are found, or if plume composition is not conclusive, the next step would be a lander mission. NASA has not yet approved or funded a Europa lander, and such a mission would likely take a decade or more to design, build, and test and launch, potentially arriving at Europa in the 2040s. A lander mission could provide more definitive results by analyzing ice samples in detail with sophisticated instruments, but would still face limitations in how deep it can sample and in ruling out contamination. A mission that drills or melts through the ice to access the ocean directly would be the most definitive approach, but also the most technically challenging and expensive. Such a mission probably would not be attempted until after lander missions have characterized the ice shell thickness and composition, and have shown that direct ocean access is necessary and feasible. We might realistically be looking at the 2050s or beyond before a cryobot and hydrobot mission could be launched and completed. This means that definitive detection of life in Europa's ocean, if it exists, might not occur until the second half of the 21st century, decades from now. That timeline assumes sustained funding and political support for Europa exploration, that technical challenges can be overcome, that no major failures set the program back, and that life exists and is detectable with the instruments we deploy. It is a long-term endeavor that will occupy the careers of multiple generations of scientists and engineers. If life is not detected in the first few missions, that would not prove that Europa's ocean is lifeless. Life might be sparse and localized, concentrated around hydrothermal vents or chemical gradients in ways that our landers and probes miss if they land or explore in the wrong locations. Life might exist in forms that our instruments do not recognize, or might use biochemistry that does not produce the biosignatures we are looking for. Life might be present in the ocean but absent from the ice and surface materials that early missions will sample, requiring direct ocean access to detect. Multiple missions sampling different locations and different depths will be needed to thoroughly search for life, and even then, proving a negative, proving that life does not exist, would be essentially impossible. We can only conclude that life was not detected in the regions and materials we sampled with the methods we used, leaving open the possibility that life exists elsewhere or in forms we did not recognize. The search for life on Europa will thus be a long-term process of gradually increasing capability and knowledge, building from orbital remote sensing to flyby measurements, to lander analyses, to eventually direct ocean exploration. Each mission will provide data that informs the next, identifying interesting locations, constraining environmental conditions, testing technologies, and narrowing the search for biosignatures. The process might take the rest of this century and could extend into the next century, a multi-generational scientific endeavor that parallels other great human projects like particle physics experiments, or genome sequencing, or climate modeling that require sustained effort over decades. The scientists who begin their careers working on early Europa missions will likely retire before definitive answers are obtained, passing the work to the next generation who will continue the search. This long-term perspective is necessary for space exploration generally and for astrobiology specifically, because the questions are profound, the distances are vast, and the technical challenges are immense. Europa is not the only target in the search for life beyond Earth, though it is arguably one of the most promising in our solar system. Mars has been the primary focus of astrobiology for decades because of its similarities to Earth, and because evidence suggests that ancient Mars had liquid water on its surface and might have been habitable billions of years ago. Current Mars missions are searching for biosignatures in ancient rocks and are laying groundwork for sample return missions that would bring Martian material back to Earth for detailed analysis in terrestrial laboratories. If life ever existed on Mars, remnants might still be preserved in the geological record, even if Mars is now lifeless. The discovery of life on Mars would be profound, though Mars life would raise the question of panspermia, whether Mars and Earth exchanged life through meteorite impacts, which would make the discovery less clearly a case of independent origin. Saturn's moon Enceladus has become another high-priority target after the Cassini spacecraft discovered that Enceladus has a subsurface ocean and is actively venting water into space through cracks at its south pole. Cassini flew through these plumes and detected water vapor, ice particles, salts, organic molecules, and even molecular hydrogen, which could serve as a chemical energy source for life. Enceladus is smaller than Europa, and its ocean is probably smaller. But the active plumes make sampling the ocean material straightforward compared to drilling through Europa's ice. A dedicated Enceladus mission could carry instruments designed specifically to analyze plume material for biosignatures and could potentially detect life without ever landing on the surface. The case for an Enceladus mission is strong, and such a mission is being considered by NASA and by international partners as a complement to Europa exploration. Saturn's largest moon, Titan, is a world utterly unlike Europa, but equally fascinating for astrobiology. Titan has a thick nitrogen atmosphere, surface liquid in the form of lakes, and seas of methane and ethane, organic chemistry driven by sunlight. Breaking apart methane molecules in the atmosphere, and possibly a subsurface water ocean beneath its icy crust. Titan is the only moon in the solar system with a substantial atmosphere and the only place besides Earth with stable liquid on its surface. The surface liquids are not water, but liquid methane at Titan's frigid temperatures of minus 290 degrees Fahrenheit. And some scientists speculate that exotic life might exist using methane as a solvent instead of water. The Dragonfly mission, scheduled to launch in the late 2020s, will send a rotorcraft lander to Titan that will fly between multiple sites, sampling the atmosphere and surface, looking for complex organic chemistry and potential biosignatures. Titan represents a different approach to habitability than Europa, and discoveries there would inform our understanding of how diverse the conditions for life can be beyond the solar system. The search for life focuses on exoplanets, planets orbiting distant stars, where thousands of worlds have been discovered in recent decades. Astronomers are developing techniques to characterize exoplanet atmospheres and search for biosignature gases like oxygen, methane, and phosphine in combinations that would be unlikely without life. The James Webb Space Telescope and future missions like the Habitable Worlds Observatory will observe exoplanet atmospheres and search for signs of habitability and life. If biosignatures are detected on exoplanets, we would know that life exists beyond our solar system, but would have no way to study it directly or to confirm the detection with alternative methods, creating an interesting situation where the strongest evidence for extraterrestrial life might come from the most distant and inaccessible locations, while the most accessible locations like Europa and Mars remain uncertain. The technology required to explore Europa and search for life in its ocean includes some of the most sophisticated engineering ever attempted, pushing boundaries in radiation-resistant electronics, autonomous systems, sampling and analysis instruments, and deep drilling or ice melting techniques. Radiation hardening is critical because the intense radiation environment at Europa would quickly damage conventional electronics through effects including single-event upsets, where a high-energy particle flips a bit in computer memory, gradual degradation of transistors and solar cells, and eventual complete failure of components. Radiation-hardened electronics use special manufacturing techniques, redundant systems, error-correcting codes, and physical shielding to extend operational lifetime in high radiation environments. Europa Clipper uses a central electronics vault with thick aluminum walls to shield critical systems, and individual components are selected for radiation tolerance. Lander missions would need even more robust radiation protection because they would spend extended time at Europa's surface rather than making brief flybys. Autonomous navigation and control systems are essential because the communication time delay between Europa and Earth is at least 45 minutes each way when Jupiter is at its closest to Earth, and longer when Jupiter is farther away. This delay makes real-time control impossible, so spacecraft must be able to make decisions and respond to situations independently. During landing, the spacecraft must detect hazards, select safe landing sites, adjust its trajectory, and control engines and parachutes, all within a few minutes without any human intervention. These autonomous systems are being developed and tested through Mars lander missions where similar delays exist, and through underwater exploration missions on Earth where communication is limited. Artificial intelligence and machine learning are increasingly incorporated into autonomous systems, allowing spacecraft to learn from experience, to recognize patterns, and to make complex decisions based on incomplete information. The instruments for detecting biosignatures require capabilities that push the limits of what can be miniaturized and deployed in space. Mass spectrometry, which identifies molecules by their mass and can detect organic compounds at very low concentrations, is a key technique for biosignature detection, but requires sophisticated vacuum systems, ion sources, and detectors that must be engineered to operate reliably in the cold and radiation of Europa. Microscopy capable of imaging at cellular or subcellular scales must function in harsh conditions and must be paired with sample preparation systems that can collect process and present samples for imaging. Spectroscopic instruments that analyze light, absorbed or emitted by samples, can identify minerals, ices, and organic molecules, and can map composition across surfaces or within ice cores. All of these instruments must be calibrated carefully, must be tested exhaustively before launch, and must operate with minimal or no maintenance for the duration of the mission. Drilling and melting technology for penetrating the ice shell is perhaps the most challenging aspect requiring development. Conventional drilling uses mechanical bits that grind through material, but this approach is slow, requires high power, generates cuttings that must be managed, and risks jamming if the bit encounters hard inclusions, or if the hull collapses. Thermal melting, where a heated probe melts ice and sinks through the meltwater, is more elegant but requires enormous amounts of energy to melt through miles of ice, and requires managing the meltwater so it does not refreeze around the probe. Radioisotope power sources, which generate heat from radioactive decay, could provide the energy for melting, but the power output is limited and the descent would be slow, potentially taking years to reach the ocean. Hybrid approaches combining mechanical and thermal techniques are being explored, as are novel concepts like using lasers to cut through ice, or using chemical reactions to weaken ice ahead of the probe. All approaches must deal with maintaining communication through the ice, with preventing contamination, and with transitioning from ice to water without flooding the probe or losing control. While missions to Europa will be robotic for the foreseeable future, the human element is crucial in designing, building, controlling, and interpreting data from these missions. Thousands of scientists, engineers, technicians, managers, and support staff contribute to planetary missions, working over decades from initial concept through design, construction, testing, launch, cruise, operations, and data analysis. These people bring their expertise, their creativity, their dedication, and their passion for exploration to a collective endeavor that no individual could accomplish. The culture of planetary science and space exploration values collaboration, rigor, innovation, and persistence in the face of challenges and setbacks. Missions take 10 to 20 years from approval to arrival at the target, longer than many careers, requiring people to commit to work they might not see completed. The emotional and psychological experience of working on these missions is profound for many participants. Scientists spend careers studying worlds they will never visit, building instruments that will analyze materials they will never touch, searching for life they may never find. The launch of a spacecraft carrying your instrument or built with your designs is a moment of triumph and terror, knowing that a decade or more of work is riding on a rocket that might explode, or on systems that might fail in the harsh environment of space. The arrival at the target years later brings tension and excitement as data begins to flow back and questions begin to be answered. Discoveries, when they occur, bring joy and validation, but also raise new questions and require years of additional work to understand fully. The potential discovery of life on Europa would be the pinnacle of many scientists' careers. the realization of a goal that drove them into the field. But it would also be bittersweet, because it would raise far more questions than it answers, and would require generations more work to understand. Public engagement and support are critical for sustaining long-term missions, because space exploration is funded by taxpayers through government agencies and must compete with many other priorities for limited budgets. Communicating the importance and excitement of Europa exploration to the public, to policymakers, and to the next generation of students requires storytelling that makes the science accessible and compelling. Media coverage, public talks, educational programs, and social media presence all contribute to maintaining interest and support. Spectacular images from missions, even if scientifically routine, capture public imagination and generate enthusiasm. The possibility of discovering life is perhaps the most compelling story in space exploration, because it speaks to fundamental human questions about our place in the universe and whether we are alone. This narrative helps sustain support through the long years and high costs of mission development and operations. The international nature of space exploration brings together people from many nations and cultures in common cause. Europa Clipper and JUICE involve partnerships between NASA and ESA and contributions from other space agencies and institutions around the world. This collaboration fosters relationships, builds shared knowledge, and demonstrates that humanity can work together on grand challenges that transcend national boundaries. The search for life in Europa's ocean is not an American project or a European project, but a human project, something we do collectively as a species seeking to understand our cosmic context. The discoveries, if they come, will belong to all humanity and will enrich human knowledge and culture broadly. This perspective, that space exploration is for all people and that its benefits accrue to all, is fundamental to the ethics and philosophy that guide how missions are conducted and how results are shared. The search for life on Europa is as much a philosophical journey as a scientific one, forcing us to confront deep questions about the nature of life, intelligence, consciousness, and meaning. What is life? How do we recognize it when it might be radically different from anything we know? If we find microbial life in Europa's ocean, does it have value and moral status? Do we have responsibilities toward it? Should we study it intensively even if that study might harm it? Should we protect it from contamination and leave it undisturbed even if that means we learn less? These are questions without clear scientific answers. They are ethical and philosophical questions that depend on our values and on how we conceive of humanity's relationship with the rest of nature and with the cosmos. Some philosophical traditions would argue that all life has intrinsic value, that living things matter morally independent of their usefulness to humans, and that we have duties not to harm life wherever we encounter it. From this perspective, contaminating Europa with Earth microbes would be wrong even if no one ever knows it happened, because it would violate the rights or interests of Europa's native biosphere. We should take extraordinary precautions to protect Europa life, and should perhaps refrain from sending missions that risk contamination until we have better understood what exists there and how to protect it. Other traditions emphasize human interests and human knowledge as paramount, arguing that the benefits to humanity of discovering and studying Europa life justify the small risks of contamination, especially since we can never completely eliminate those risks. From this perspective, we should proceed with exploration as quickly as technology allows, taking reasonable precautions but not letting concerns about contamination prevent us from pursuing knowledge. The question of whether life is unique to Earth or is common in the universe has been debated by philosophers and theologians for centuries. Ancient Greek philosophers speculated about a plurality of worlds, inhabited by other beings, while medieval Christian theology largely rejected this idea based on interpretations of creation narratives that placed Earth and humanity at the center of God's attention. The Copernican revolution displaced Earth from the physical center of the cosmos and suggested that our world might not be special or unique, opening the possibility that other worlds might also harbor life. Modern science has progressively shown that the materials and processes that led to life on Earth are not unique, that organic chemistry occurs throughout the universe, that planets are common, and that the conditions favorable for life likely exist on billions of worlds. The discovery of life on Europa would be another step in this Copernican process, removing humanity further from the center and showing that Earth is not the only living world even in our own solar system. For some, this decentering is liberating and inspiring, a recognition that we are part of something vast and wonderful, that the universe is richer and more interesting than anthropocentric views suggested. For others, it might be disturbing or might challenge cherished beliefs about human uniqueness and purpose. Religious traditions would need to integrate the reality of Europa life into their theological frameworks, considering whether scripture and tradition have resources to address life beyond Earth, or whether new interpretations and developments are needed. Some traditions might embrace the discovery as evidence of the richness of creation and of the divine working throughout the cosmos. Others might struggle with questions about whether non-human life has souls, whether divine revelation is specific to humanity or universal, whether concepts like sin and redemption apply to other living beings. These theological questions would be debated in churches, mosques, temples, and academic institutions, and would likely lead to diverse interpretations and responses across and within religious traditions. While Europa life, if it exists, is almost certainly microbial and non-intelligent, the discovery would make the broader search for intelligent life in the universe more hopeful and more urgent. If life has emerged independently, at least twice in our solar system, on Earth and on Europa, that suggests that life is common on cosmic scales and that the galaxy likely contains billions of living worlds. Among those billions, some fraction would likely evolve intelligence and technology, creating civilizations capable of communication and perhaps even interstellar travel. The search for extraterrestrial intelligence, SETI, which uses radio telescopes to listen for signals from distant civilizations, is based on the hope that such civilizations exist and are trying to communicate. Europa would not directly contribute to SETI because any life in Europa's ocean would have no access to astronomy. I would not know that a universe exists beyond their ocean, and could not develop radio technology in a water environment. But Europa would show that the origin of life is not impossibly rare, making the case for SETI more compelling. The question of what we would say to an intelligent alien civilization if we made contact, what we would want them to know about humanity and Earth, is one that has engaged scientists, writers, and the public for generations. Spacecraft leaving the solar system, Voyager and Pioneer, carry plaques and golden records with information about Earth and humanity. Messages in a bottle for any distant civilization that might someday intercept these ancient probes. These messages include images, sounds, music, greetings in many languages, mathematical and scientific information, attempting to convey in universal terms what humans are and what we value. But designing such messages is extraordinarily difficult because we have no idea what alien intelligence would be like, what concepts would be comprehensible, what would be interesting or meaningful to beings with no shared evolutionary or cultural history with us. Would they understand images? Would they perceive light and sound the way we do? Would mathematical or physical constants be the universal language we hope? Or would even these be interpreted differently by minds that evolved in alien environments? The discovery of even microbial life on Europa would not answer these questions about intelligence and communication. But it would provide at least one example of alien biochemistry to compare with Earth, a starting point for understanding how diverse life can be. If Europa life uses similar biochemistry to Earth, we might conclude that there are constraints that push all life toward similar solutions, which might mean that intelligence, if it evolves, might also have commonalities across different evolutionary histories. If Europa life is radically different, using different chemistry or information storage or metabolic pathways, that would demonstrate that life is more diverse than we imagined, and would suggest that intelligence might also be more diverse and harder to recognize or communicate with. Either outcome would inform how we think about intelligence in the universe and how we approach the search for it. The dream of contact with intelligent aliens, of joining a galactic community of civilizations, has been a staple of science fiction and scientific speculation for over a century. It represents a hope that we are not alone, that the cosmos contains others like us with whom we could share knowledge and culture, others who have solved problems we struggle with, and who might help us survive and thrive. But it also represents a fear that contact might go badly, that advanced civilizations might be hostile or exploitative, that we might be placing ourselves at risk by advertising our presence. The Fermi paradox, the apparent contradiction between the high probability of alien civilizations and the complete absence of evidence for them, has been explained in many ways, including that civilizations tend to destroy themselves before reaching interstellar capability, that they choose to remain hidden, that they exist but are too far away for us to detect, or that intelligence is far rarer than we hope. Europa cannot resolve the Fermi paradox, but by showing whether life is common or rare, it can constrain some of the possible explanations. Looking ahead, the exploration of Europa will likely continue throughout the remainder of this century and beyond, with each generation of missions building on the discoveries and technologies of the previous ones. If Europa Clipper and JUICE find strong evidence of a subsurface ocean and detect organic molecules or other signs of habitability, the next step would be lander missions to analyze surface and ice composition in detail. These landers would be sophisticated semi-autonomous laboratories capable of drilling meters into the ice, analyzing samples with multiple instruments, and transmitting data back to Earth for years. If lander missions detect biosignatures or confirm that the ocean is habitable and energy-rich, the justification for cryobot missions would become overwhelming despite the technical challenges and costs. By mid-century, we might see the first attempts to penetrate the ice shell and directly sample ocean water, either through melting probes or through accessing naturally occurring cracks or thin ice regions where the ocean is closer to the surface. If life is detected in Europa's ocean, the exploration would enter a new phase focused on understanding that life in detail. What is its biochemistry? How does it metabolize and reproduce? What is its genetic system, if it has one? How diverse is it? Does the ocean contain multiple species and complex ecosystems, or just single-species microbial populations? How does it compare to Earth life? Are there molecular or structural commonalities that suggest universal principles of biology? These questions would require many missions with increasingly sophisticated instruments, probably including sample return missions that bring Europa water or ice back to Earth, where the full capabilities of terrestrial laboratories could be applied to studying the samples in detail that spacecraft instruments cannot achieve. Sample return from Europa would be extraordinarily challenging, requiring a lander that can collect samples, a launch vehicle to escape Europa's gravity and Jupiter's gravity well, a return spacecraft for the multi-year journey back to Earth, and containment systems to ensure that any Europa life does not escape into Earth's environment, where it might cause unpredictable ecological effects. The development of technologies for Europa exploration would have applications beyond Europa. The radiation-hardened systems, autonomous navigation, ice-penetrating instruments, and biosignature detection capabilities developed for Europa could be applied to exploring other icy moons, including Enceladus, Ganymede, Callisto, and the moons of Uranus and Neptune, which also appear to have subsurface oceans. The lessons learned about how to search for life in extreme environments would inform missions to Mars, Titan, and eventually to exoplanets if we ever develop the capability to send probes to other star systems. Europa is, in some sense, a test case, a relatively nearby example of the kind of environments that might be common throughout the galaxy. Places where life hides beneath surfaces in liquid water oceans, sustained by chemical energy rather than by starlight. Learning how to explore Europa and how to detect life there is learning how to explore a class of worlds that might be among the most common habitats for life in the universe. The economic and political challenges of sustaining a multi-decade or multi-century exploration program should not be underestimated. Planetary science budgets are limited and must support many missions and investigations competing for resources. Europa missions are among the most expensive planetary science missions due to the difficulty and distance, and each mission costs billions of dollars and takes decades to complete. Maintaining political support for such expensive long-term projects requires demonstrating value and results, requires engaging the public and policymakers, and requires weathering changes in administration and in national priorities. The history of planetary exploration includes many examples of missions that were cancelled or delayed by years or decades due to budget constraints or political decisions. Europa exploration will need champions in the scientific community, in space agencies, and in government who can make the case that the search for life is worth the investment, and who can sustain momentum through the inevitable challenges and setbacks. Imagine the moment when data from a Europa lander or from a hydrobot in the ocean is transmitted back to Earth, and scientists examining the data realize they are seeing evidence of life. The moment would likely be quiet and uncertain at first, not a sudden revelation but a growing realization as multiple analyses converge on the same conclusion. A mass spectrometer might detect organic molecules with structures that are characteristic of biology. A microscope might image structures that look like cells or colonies. Isotopic measurements might show fractionation patterns that are best explained by metabolic processes. No single measurement would be definitive, but together they would build a case that something in the samples is alive or was alive. The scientists would be cautious, checking for contamination, running control experiments, searching for alternative non-biological explanations, because the claim that life has been found beyond Earth is extraordinary and requires extraordinary evidence. As the evidence accumulates and alternative explanations are ruled out, the excitement would build within the team analyzing the data. Confidential discussions would begin about whether the results are strong enough to announce, whether additional experiments are needed, how to communicate the findings to avoid premature or misleading claims. The process from initial detection to public announcement might take months as the team carefully validates the results, prepares scientific papers for publication in peer-reviewed journals, and coordinates with space agencies and institutions. The announcement, when it comes, would likely be made simultaneously through scientific publication and through press conferences and media outreach, ensuring that the scientific community and the public learn of the discovery at the same time. The immediate response would be global and intense. News media around the world would cover the discovery prominently, interviewing scientists and experts, explaining what was found and what it means. Social media would explode with reactions ranging from excitement to skepticism to humor to philosophical reflection. Scientists in astrobiology and related fields would scramble to analyze the data as it becomes public, writing commentary and response papers, proposing new theories and interpretations. The scientific community would engage in vigorous debate about the evidence, with some accepting the discovery enthusiastically and others remaining skeptical and demanding more data. This debate is healthy and normal. It is how science self-corrects and ensures that extraordinary claims are thoroughly tested before being accepted as established knowledge. Religious and philosophical leaders would offer interpretations and reflections on what the discovery means for understanding humanity's place in the universe and for religious teachings about creation and purpose. Some would see the discovery as confirmation that God's creation is vast and diverse, that divine creativity extends beyond Earth, that we should respond with humility and wonder. Others might struggle with reconciling the discovery with theological views that placed humanity at the center of divine attention. Educational institutions would develop new curricula incorporating the discovery, teaching students about Europa life and about the methods used to detect it, inspiring a new generation of scientists and explorers. The discovery would become part of human culture and would be referenced in art, literature, film, music, and philosophy as humanity grapples with the implications of knowing we are not alone. The search for life in Europa's ocean is one of the great adventures of our time. A quest that combines the best of human curiosity, ingenuity, and determination in pursuit of answers to profound questions. It is a search that requires patience because the timescales are long and the challenges are immense. It requires collaboration because no individual or nation can accomplish these missions alone. It requires vision, because we are working toward goals that we might not achieve in our lifetimes, but that will benefit future generations. It requires humility, because we are searching for something we might not recognize and might not find, even if it exists. And it requires courage, because we are venturing into the unknown and must accept the possibility that the ocean is lifeless, that we will spend decades and billions of dollars in a search that yields no life, only the knowledge that we looked and learned what we could. But the potential rewards justify these challenges and risks. If life exists in Europa's ocean, finding it would transform our understanding of biology, of how common life is in the universe, of whether we are alone or are part of a living cosmos filled with organisms in environments we are only beginning to imagine. It would show that the conditions for life are not impossibly narrow, that life can arise and persist in darkness and cold, sustained by chemistry rather than by sunlight, using energy from planetary interiors rather than from stars. It would suggest that icy moons, of which there are many in our solar system and presumably countless numbers in other star systems, are potential habitats for life, and should be targets for exploration and for the search for intelligence. It would place humanity in a larger context, not as the unique product of Earth's history, but as one expression of a universal phenomenon, life emerging and evolving wherever conditions permit. Even if life is not found, the search itself is valuable. The missions to Europa will advance technology, will train scientists and engineers, will produce knowledge about planetary processes and about how worlds form and evolve. The data returned will be studied for decades, yielding insights we cannot predict and raising questions we have not yet thought to ask. The experience of building and operating these missions will inform future exploration of other worlds, will develop capabilities and expertise that can be applied to many endeavors. The inspiration that the search provides, the way it captures imagination and encourages young people to pursue science and exploration, is itself a return on the investment even before any discoveries are made. Humanity is an exploring species. We are driven to see what lies beyond the next horizon, and Europa represents a horizon that calls to us with the possibility of discovering life, of finding kindred organisms in the darkness of an alien ocean. The journey to Europa's ocean will be measured in decades and in generations. A long road from where we are now with orbital missions and flybys to where we want to be with landers and submarines exploring the ocean directly. Each step forward will be celebrated. Each data return will be analyzed with care and excitement. Each discovery will raise new questions and motivate further exploration. The scientists and engineers working on these missions are building something that extends beyond their individual careers, contributing to a human endeavor that spans generations and that represents our species at its best: cooperative, curious, persistent, and hopeful. When the data finally arrives from the dark waters of Europa's ocean, whether it shows life or shows only chemistry and physics, we will know that we tried, that we reached across the solar system to explore a world utterly unlike our own, that we asked the question and sought the answer with all the skill and dedication we could bring to bear. In the cold darkness beneath Europa's ice, in an ocean that has never seen sunlight, in water kept liquid by the flexing of gravity across billions of years, something might be swimming. Something might be metabolizing and growing and reproducing, living a life shaped by conditions we can barely imagine, thriving in an environment we would find instantly lethal. If that something exists, it is waiting to be discovered, waiting for us to develop the technology and the will to pierce the ice and to shine our lights into those dark waters. And when we do, when human instruments finally reach that alien ocean and begin to record what exists there, we will have taken one of the most important steps in human history. The step from knowing only Earth life to knowing that life exists elsewhere, that biology is universal, that we are not alone in the cosmos. That moment, when it comes, will echo through the rest of human civilization, will be remembered for as long as humans tell stories, will mark the time when we learned that Earth is not the only living world, that somewhere out in the darkness, life found a way.